This is the recording of the second half of the 3.2 lecture. This version of the recording will focus on using the TI Nspire calculator to do our calculations having to do with the least squares regression line. Earlier in our lectures, we talked about a regression line as being a line that somehow models the data. Now, how do we know that we have the line that goes through the data the best? Well, the experts believe one of the best ways to find a model through the data is to do something called the least squares regression line. And here's the basic idea. Each data point in our scatter plot has a residual. For example, this data plot right here has a residual, but this residual happens to be negative. This data point here has a residual, but its residual happens to be positive. If you sum up all the residuals, you end up getting 0. So simply adding the residuals isn't great. So in order to make it so that when we do something with the residuals, the error of the prediction, that when we add up everything, we don't get a 0, the experts have decided that the best way is to square the residuals and then add them up. And they say that they think the model that gives us the best fit is the one that minimizes the sums of the squares of the residuals. And therefore, they call this method the least squares regression line. The line that makes the sums of the squares of the residuals as low as possible. We are now going to see how to use the TI Nspire calculator in order to find the least squares regression line. Now, in the previous example, we had body weight and backpack weight, but in this example, we're going to look at the truck data from the previous lecture. Now, here's the idea. We've got a whole bunch of variables that are going to be our explanatory variables, our miles driven, and we've got a whole bunch of a variable which has a whole bunch of values, which is going to be our response variable, the price. And we're going to get this data into our calculator. So I'm going to bring up my calculator, right? I'm going to start a new document. I'm going to add a page to that document, which is a list and spreadsheets page. And in this list and spreadsheets page, I'm going to create 2 columns. One of them is going to be called miles. And the other one, let me hit enter and then go over. And the other column is going to have our Y variable price. And now I can start entering my data for the miles. 70, 5, 3, 129, 4. All right. And once I get done with the miles, I'll do price. Now, to save some time, okay, you can pause this video, enter your data, but I'm going to simply switch to a document in which I have already put the data, and that data is in a document I just call truck. And now we have all of the data into our our calculator. Where do we go from here? Well, how about we take a quick look at the scatter plot of this data? I'm going to add a page into my document, control, and then plus page. I want to have that page be a data and statistics page. Hit enter. And now we're going to ask the calculator to organize our data. We want the explanatory variable to be miles driven. So we're going to bring our cursor down to the bottom part of this screen, click in the middle of our touchpad, and we're going to choose miles as our X variable. And that gives us a dot plot of the different miles from our data set. Now, if we take our cursor and go over to the far left-hand side, click in the middle of our touchpad, and then choose price, it creates the scatter plot for our data, right? And we saw, as in the earlier lecture, that that data set looks like a strong negative linear relationship. But let's say we want to find the equation that best goes through that data. To do that, we're going to add another page to our document, add a page. It's going to be a calculator page. And the calculation that we're going to do is under Menu, Statistics, and we're going to do a stat calculation. And the stat calculation that we are going to do is a linear regression. And again, we want it to be in the statistical form, A plus BX. So I'm going to choose that. And it asks us, well, what's our X data? If we click on the right arrow on our touchpad, pop-up menu comes up. We're going to say our X data is miles. Hit enter. Hit tab to go to the next one. Right arrow. And what's our Y data? Our Y data is the price data. And everything else can be left the same. We say OK. And we get this printout. And this printout informs us that the A value, the y-intercept, is the 38,257 that we talked about earlier. That the slope value is negative 0.1629, and it gives us the R value, the correlation, which is negative, which we expect because it's a negative relationship. And this one is pretty close to -1, indicating that there's a strong relationship. So if we go back to the notes, we have got on our display that the A value again was 38,257.1, that the B value was negative 0.1629, the R value was 0.8150, and there was an R squared value, which we're going to talk about a little bit, and it is 0.6642. And again, we'll talk about the R squared value in a little bit. Now, if we want to see that line going through our data, then we can go back to the scatter plot. I'm going to hit Control left arrow to change what page I'm looking at. And we can go ahead and say, I'd like to see that line of best fit going through the data. We choose Menu. We choose Analyze, which is option 4. We're going to be looking at the regression. And again, we can choose Show Linear, A plus BX. And now our linear regression line is now shown going through our data. What's going on with the calculator when it does all of that work to calculate the least squares regression line? It's actually surprisingly simple. The computer, the calculator, is using values that we've already talked about in previous lessons. To find the slope, it takes the standard deviation of all the y values, the standard deviation of all the x values, and it multiplies that ratio by r, the correlation. And again, in a previous lecture, we found out how to find the r value. Now, in order to find the the A value, the y-intercept, there is a there is a assumption made for the least squares regression line that there's one known point that has to be on the regression line, and that is the average of all the x's and the average of all the y's. It uses the fact that if you know a point and you know a slope, you can calculate the y-intercept. And so the y-intercept ends up being calculated thus. So the least squares regression line assumes that we're going through the point x bar, y bar, right? Now, the other thing that's going on here is that the slope has, again, this regression line, this calculation, which means if we think of this as rise and run, if I move one standard deviation in the x direction, then the rise in the predicted line is exactly r times the standard deviation of the y data. So every increase in one standard deviation in x leads to an increase of r standard deviations in the y variable. So given just a little bit of information, we should be able to hand calculate the value of the slope and the y-intercept. So a random sample of 15 high school students were selected from the U.S. Census at School database. The foot length in centimeters and the height in centimeters of each student in the sample were recorded. The data used to investigate the relationship between foot length and height. The mean and the standard deviation of the foot lengths are given. The mean and the standard deviation for the heights are given right here. Okay, and the correlation is given. Can we find the equation of the least squares regression line for predicting height from foot length? Okay, so our job is to find y hat a plus b x, which could also be thought of as try to find the predicted height based on the foot size, the foot length, right? And what were we told? That b is equal to r times the standard deviation of y divided by the standard deviation of x. And in this case, we have a positive correlation. And we're going to multiply it by the standard deviation of y, 10.69, and divide it by the standard deviation of x, 2.71. And if we go to our calculator, and I'll want to be on a calculator page, I can do that calculation, 0.679. Let's multiply that by the fraction 10.69, all divided by 2.71, and we get 2.6 2.67842. All right. Let's go back to our notes. 2.67842. So for every additional centimeter of foot length, we expect the person's height to increase by about 2.67 centimeters. Now let's calculate A. Remember the formula for A was that it was y bar minus b times x bar, which in this case Y bar is 171.43, sorry, minus 2.67842, and we're going to multiply that by X bar 24.76. So let's go ahead and put that in. So I'm going to have 171.43 minus, and I'll just pop up and grab that number. And we're going to multiply that by the foot length, average foot length of 24.76. And we get 105.112. So A is 105.112, meaning that our predicted height can be found by taking 105.112 and adding to it 2.67842 times the foot length. For every increase in of 2.71, how much do we think the height is going to change? Well, 2.71 happens to be the standard deviation of X. So we think that the change in height, or change in predicted height, is going to be, since I've changed one standard deviation in the X direction, it's going to be R times the standard deviation of Y. And again, R is 0.679, and we'll multiply that by 10.69. 679 times 10.69, and we get 7.25851. 7.25851 inches. And again, that's how much we think the height would increase if the foot size increased by one standard deviation. So it says one of the first principles of data analysis was to look over the overall pattern and look for striking departures from that pattern. One way that we do that is to look at the plot of the residuals. Now we know that the residuals represent how much error is there between the actual data and the one that the model predicts. We can make a plot of those residuals by keeping the x-axis the same, but instead of having our response variable, we can just change our response variable to the residuals. All right? And for every dot that's on the residual plot, it maps back to some point in our original scatter plot. This point was really, really close to line. It has a really small residual, and there it is. This plot right here is about where X is 42,000, and it's quite a bit below the line. That must be that point right there. So for every point in the residual plot, there's a corresponding point in the original scatter plot. Now, what does it mean to interpret the residual plot? Well, we're looking for two things to confirm the linearity of the original data. One, when we look at the residual plot, there should be no obvious patterns because the randomness and it's inherent into these predictions should be spread evenly throughout all of the data. And if we look here, I don't see any particular pattern. That's good. And we hope that the residuals are relatively small in size. Now, in this case, the residuals run from about 9,000 at the high end to about and negative 8,000 on the other. So is that a small residual when we're trying to predict the cost of a truck? I'm not really sure. Here's what patterns look like when we're doing residual plots. Here is some data, original data that's clearly not linear. And when we do the residual plot, pretending that it is linear, we see a clear pattern in the residual plot. Our, our, our conclusion is therefore the original data are not linear. Okay. Now, the residuals tell us one other thing. Well, if we find something called the standard deviation of the residuals, we can find what's referred to as the typical or average prediction error. So when we're, let's say, using only miles data to predict the price of a truck, we know that we don't get the right answer all the time, but we'd like to know, on average, how close is it to being the right answer? And we do so by calculating, again, the standard deviation of the residuals. That calculation is found by adding up the squares of all the residuals, dividing it by the number of data items minus 2, and then taking the square root of those. So let's calculate the sums of the squares of the residuals. Sorry, let's calculate the standard deviation of the residuals if we are told that the sums of the squares of the residuals is a whopping 461,300,000. So S is the symbol that we use for the standard deviation of the residuals. Its formula is, again, the square root of the sums of the squares of the residuals divided by n minus 1. And in this case, that's 461,300,000. Divide that by, in this case, there were 16 trucks in their data set. So it's the square root of 461,300,000 divided by 14. Okay. And let's go and calculate that on our calculator. Square root 461,300,000. And let's go ahead and let's divide that by 14. I hit the control enter. I hit control enter so we get a decimal version of that answer. And we get 5,740 approximately. 5,740. So how would you feel about when I use this model that we're off by about almost $6,000? Well, we might say, yeah, mileage helps us predict, but it's not everything in terms of predicting the value of a truck. So we're going to go through how we could have calculated the standard deviation of the residuals by hand. Also, how to produce a residual plot on the TI Nspire calculator. We already have our data in our calculator. Now, the calculator has gotten better in the time that we've made these notes. We are no longer going to do this. I'm going to show you how we can get at the residuals more directly and create those residual plots. So, if we go to the calculator, all right, under var, there's a pop-up menu of all the kinds of things that have been calculated in this document. And one of the things that got calculated was the residuals. Remember, we did a linear regression, and the action of doing a linear regression is minimizing the squares of the residuals. We actually have in our possession all the residuals for every data item in our data set, which means if I add a page, let it be a data and statistics page, I could say what I want to see is my X data, our miles data, graphed against our residual data. And that is our residual plot. Remember that one data item that was pretty close to the line? Well, there it is again with its X value and its residual value. It was only off by $458 in its prediction. Now, how about calculating the um, the standard deviation of the residuals? Well, we remember that the formula for that was the square root, and above here we had the sums of the squares of the residuals. I'll go to vars, I'll go down and choose stat resid, I'll go I'll type in the word sum, parenthesis, then I'll go to vars and choose stat resid, and then I will add a squared onto it. And that will sum each of the residuals and then add them up. And then we'll divide that again by n minus 2, which in this case is 14. And there we have it. There is our standard deviation of our residuals. Again, a prediction error. One last thing we want to look at, and that is the R squared value that we alluded to earlier. The R squared value is called the coefficient of determination, and it's got a really interesting property. It says the standard deviation gives an estimate of the average size of the prediction error, but R squared tells us the fraction of the variation in the Y that can be accounted for the linear regression of Y on X. Let me see if I can explain this using the information that we collected earlier. Earlier, we found that the R squared value, and where is that? The R squared value for the truck data was 0.6642, okay, or about 66%. What this means is that about 66% of the variation in the price can be explained by the miles driven. Now, note that 66% is not 100% because there are other things that factor into the price of a truck. Sure, miles driven is a big one, but does it have rust or does it not have rust? Is it a particular obnoxious shade of chartreuse? Was it driven by a smoker? Had it been in an accident? All these things factor into the price, but aren't miles. Miles factors can account for 66% of the differences, but the other 34%, let's say, are accounted for with other things. So the R squared value gives us that, again, fraction of the variation of Y that can be accounted for with X. All right. Back here. All right. Let's do one more example. It says, in this last example, suppose a new student is assigned to the last minute to the group of 8 hikers. How would we predict their backpack weight? Well, we know how to predict it using the line if we have a body weight. But if we don't know their body weight, what's the most reasonable thing to do? And the answer is to use the average backpack weight. It's based on information that we have. We have the average, but we don't know the variability. So average backpack weight would probably be our best guess. So our best strategy is to use mean backpack weight to make our prediction if we don't have a body weight. All right. Now, most times professionals do not use Desmos or TI Inspires to calculate regression. Um, Often they use uh, software. One piece of software that can be used is called Minitab. It's a data statistical analysis software. And the Minitab, if you ask it to do a linear regression, it would print out this table. And all we want to see from this is that things that we've just talked about are in this table. For example, coefficient is like the number in front of a variable. The coefficient on miles driven is right here, and that's the slope. Sometimes there is no variable, so it's the coefficient, really is called the constant, and there's our y-intercept. Here's our standard deviation of the residuals, our average error when we use the prediction model, and here is our R-squared value. The amount of variability that can be in the amount of variability in y that can be explained by x. All right. By the way, if you want to find out the R value, go ahead and take the square root of the R squared value, but just remember it could be a plus or a minus. Remember, our slopes were a negative slope, so the R value would be negative. Let's go on to our next example. In this next example, how can we interpret printouts from a computer? Okay, how well does the number of beers a person drinks predict his or her blood alcohol content? 16 volunteers with an initial BAC of 0 drank a randomly assigned number of cans of beer. 30 minutes later, a police officer measured their BAC. Least squares regression was performed on the data. The scatter plot was then added, the residual plot was computed, and some output was provided. All right. So, first question. What is the equation for the least squares regression that describes the relationship between beers and blood alcohol content? Okay, well, we are trying to predict blood alcohol content. So BAC predicted is our y-intercept, which in this case starts with 0.012701 plus our slope, which could be found there, 0.017964. Again, it's the coefficient on beers. And again, our x variable is beer or beers. Right? And by embedding those and not using x and y's, I have defined the variables that I'm using. Interpret the slope of the regression line in context. Okay. Well, our standard information for every additional, in this case, in our x variable, beer, there is a 0.017964 increase, because the slope is positive, in the predicted BAC. And I'll just put it in on average. Okay, what's the correlation? Well, let's take a look what they give us. Oh, they gave us, there's an 80% R squared value. So the correlation is the square root of 80%, and that ends up being 0.894, which is a pretty strong R value. Make sure, again, the slope is positive, so that R value is positive. Is the line appropriate model for these data? what information tells us that? Well, let's take a look at the scatter plot. Scatter plot of BAC versus Beers shows okay, and I'm looking here now, a linear pattern. So that's good. Okay. And by the way, by referring to what I'm looking for, that's again an idea called linkage. What happens when we look at the residual plot? Residual plot, residual plot shows no pattern. Well, this combination of linear pattern in the original data and no pattern in the residual plot leads us to the conclusion that the data are linear, or the relationship is linear. Okay. What was the BAC reading for the person who consumed 9 beers? Okay. Well, let's see if we can figure that out. What do we see? BAC for someone who 9 beers looks like it's right about there. And I would guess that that is about 0.19. So the BAC is 0.19 for the person who consumed 9 beers. Okay. Notice it didn't ask for the predicted BAC. It said, what is the person who, what was it? Okay. And it ends up being, yeah, I'd say right around 0.19. All right. Home stretch. There's some cautions as we finish this up. Just want to make sure that you understand, it's easy to calculate these things on the calculator, but that doesn't mean it's always appropriate. Couple of things to be mindful of. When we do these calculations, it matters which one is your x variable and which one's your y variable, not for the r value, but for your slope and for your y-intercept. You will get different predictions if you switch the two around. Okay? So just remember the r value, r square value will be the same, but the lines will be different if you switch your x and your y values. Second idea, correlation and regression lines only describe linear relationships. Okay, just because you got a regression line equation doesn't mean it's appropriate to use it. It's only appropriate to use it if the data are linear. So for example, all of these four data sets, they all have something in common. They all produce the same least squares regression line, but it looks like only one of them, data set A, is it anywhere appropriate to use as a linear model for? Um, because this guy's an outlier, it's probably not appropriate to use a linear model unless you remove that data point. This is a clear data curve pattern, and this doesn't look much like um, a linear relationship at all. Item number 3, correlation and least squares lines are not resistant. This outlier will affect the quality of the prediction model. Okay, one unusual point can greatly change the value of R. Okay, so if we're going to talk about how outliers can have that effect, um, we better get a handle on what we mean by an outlier. For outliers for linear models, we don't have a rule like the 1.5 IQR rule, but we can say that an outlier lies outside the overall pattern of the other observations. Points that are outliers in the y direction, but not the x direction, have large residuals. Other outliers may not have large residuals. I'll show you that in a second. Second, an, an observation can be an outlier and it can be influential if removing it would make a marked change in the results of the calculation. Points that are outside the x variables values for the scatter plot are often influential. Let's look at those two ideas in the context of a data set. So we have a data set that collected the information of how old the child was when they began talking, and then later they also calculated some measurement of mental ability. So we have data. Here's a kid who at 15 months for their first word, and then their later Gazel score. So what do we have to? Is there a relationship here? Well, let's plan on how we might answer that question. We can do a scatter plot. We can do, if it's in a linear form, we can do a least squares regression line, and we can look at the R value. We can look at the residual plots. Okay. Now, when we look at this data, please note that there are two pairs of children that have exact scores. They end up having bigger effects, even though they only show up as one dot on the scatter plot. It says scatter plot shows a negative association. The R value is 0.64, right? But let's take a look at a couple of outlying children. Okay, so here's our scatter plot of our original data. No, child number 19 seems unusual. It has a large residual because it's so far away from the prediction line. Child 18, close to the residual, the prediction line, but far away from the rest of the data. All right, so this is an outlier because it's away from the general trend. This is an outlier. Okay, but this outlier is also an influential data point because moving it will drastically change the slope and the R value. Right? If we ignore these two, do we see a general random pattern? You bet we do. All right. So how well does the least squares fit the line? The residual plot looks pretty good. Standard error is 11, but that's with the data, those two outliers included. We probably can get the error, the standard deviation of the residuals, the error down smaller if we were to remove those two outliers. So we think in general, we might think this is pretty good. We might hesitate making predictions because the error is so large. We may want to think of rerunning the data without those large outliers, the unusual kids. All right. Last point on things to worry about with regression, and that is association does not imply causation. Just because there's a relationship, a high correlation, it doesn't mean that one thing's actually associated with the other or causes the other. For example, a serious study once found that people with two cars live longer than people with one car, and owning three cars is even better, and so on. Is there substantial positive correlation, or there is a substantial positive correlation between the number of cars and length of life? And the answer is, this doesn't mean that if I want to live longer, I should own more cars. The basic meaning of causation is that by changing X, we can change Y, but we don't think we can lengthen our lives by owning more cars. The study used number of cars as a quick indicator of wealth. Well-off people tend to have more cars. They tend to live longer, probably because they're better educated, take better care of themselves, and get better medical care. So watch out. Just because we have a strong correlation doesn't mean that we have causation. So we've learned a lot in this section, and that concludes our 3.2.2 lecture.